Hey, class, Mr. Bean here. Wanted to go over problem 5.4, which is in video 42. Give you guys some hints on here, and also talk a little bit more about force and displacement and the cosine of theta. All right, so in this problem here, you find out is that you're given force versus displacement, graph below, for a net force applied horizontally to an object of mass m, initially at rest on a frictionless surface. Determine the object's final speed in terms of this, this, and this. You may assume that the force does not change its direction. So that means we're going to have velocity equal to something that has F, R1, R2, and R3 inside of it. All right. So first of all, what we need to do is we'll have to use the work kinetic energy theorem. So the net work that's done here, we'll say net work. The net work that is performed is going to have to be we'll say it's going to be the change in kinetic energy. Okay, that's the formula here. Change in kinetic energy, and let me get an eraser here. Okay, it's going to be change in kinetic energy, but also is that it's also equal to the area under the curve too as well. Okay, so the work done is going to be the area under the curve and equals the change in kinetic energy. All right, so what does that mean? So area under the curve is we have triangle area 1, here's area 2, and here is area 3. Okay, and all this area here has to equal the change in kinetic energy. All right, so the area, so let's go ahead and do it here. So the area of this here is a triangle, and it looks like it's going to be 1/2, right? So it's going to be 1/2 the base, which is R1 times force. We'll just use F here for the force, maximum force, okay, plus area 2. So area 2 is just a rectangle here, just length times width, but it's this width here and times this force. So we'll go ahead and go force here we'll say the height of this here times, we have to say R2 minus R1 like that, okay? And we have to add it to this area here, which is another triangle, and it's going to be 1/2, okay? Now the base is going to have to be, was it R3, right? Minus R2, okay? And the height is going to be force, okay? And this has to equal the change in kinetic energy. Okay. All right. So now we can assume that's going to start from rest. So the kinetic energy is going to be just 1/2 mv squared, like so. Okay, it starts from rest. Okay, 1/2 mv squared. All right. So first of all, I see these 1/2s here. I don't like fractions. So let's multiply everything here by 2. So we're going to multiply by 2. Okay, so multiply everything by 2. So when we do that, we'll have here's R1, right, times F, like so, plus, uh, this is going to be 2F, right, 2F here, times R2 minus R1, like so, plus, this is just going to be, what, R3 minus R2, right? Times F, or just F here still. There's still an F here. Oh, no, we already got that F there. Okay. It's going to equal uh, just mv squared. All right. So let's do some simplifying here. So this is going to be R1F here, right? Okay, plus, okay, let's do the distributive property here. And that should be 2FR2, right? Minus 2F R1, good, plus just R3 minus just R2, right? And it should be F here, right? We should have a F here and an F here, okay, is equal to mv squared. All right, now let's do some simplifying here. So here's an R1 here, and here's an R1 here, and no other R1s. So RF minus 2 R1F is just going to be minus F R1. Okay, so we got rid of this term here and this term here. And let's see what else we got. We got plus here. So here's 2F2, and here's a minus F R2 right here. So it's just going to be F R2 here. Okay, that's gone and that's gone. And we just have, all we have left now is just F R3. Okay, and this has to equal mv squared. All right, so now what we can do is kind of rearrange it, factor out the f and divide by m. So we're going to factor out the f, divide by m here. Okay, rearrange it so it's going to be r3 plus r2, right, minus r1 is equal to v squared. Therefore, v is going to equal the square root of, here's F, the maximum force divided by the mass. It's going to be R3 plus R2 minus R1. All right, and that's how we do that problem there. Okay, so you make sure you do this by yourself. Now one more thing here is this: if we have some box here, right? Let's say there's some box, and let's say the displacement is in this direction. So we'll say this is delta x. It's in this direction, and let's say the applied force is in this direction. Okay, well, it looks like here we have 90 degrees, right? This is 90 degrees. Okay, so work done is going to be force, right? Times delta x times the cosine, right, of 90 degrees. Now, cosine of 90 is 0. So there's 0 joules of work being done whenever work and displacement are perpendicular. See, so some people miss that. All right, that'll do it, and we'll talk later. Take care.